Hey, you. Ever stop and really think about those silver fillings? Lots of us have them, right? Or know someone who does.
Yeah, they were pretty common.
Well, today on the deep dive, we're going to unpack the surprisingly complex story behind dental amalgam. That's the professional term.
That's right. We're going way beyond just calling it a filling.
Exactly. We've got some great source material here, bits from a video lecture, a detailed PDF doc.
Mm-hmm. Both really digging into the nuts and bolts of amalgam, what it is, how it works, and crucially, how dentists handle it.
Right. So our mission, if you will, isn't just to skim the surface. We want to understand why it's been such a workhorse in dentistry.
Yeah, what makes it tick, its strengths, its weaknesses, maybe clear up some myths too.
Totally. You might actually be surprised by some things, like mercury's role, or that there are different kinds of amalgam.
And how much technique matters for making it last. It's not just plug and play.
Okay, let's dive in then. What is dental amalgam, fundamentally?
Well, okay. At its core, amalgam's an alloy. Like brass is copper and zinc mixed.
Yeah.
So amalgam is a mix of metals, but the defining thing is one of those metals is always mercury.
So the silver filling name is just about the look.
Pretty much. It looks silvery, but the actual recipe is more complex than just silver.
Okay, so what is in the mix, typically?
Well, you've got mercury, which is like roughly 50% by weight.
Mm.
Huge chunk.
50%? Wow.
Yeah. Then there's silver, usually around, say, 30-ish%. Tin's in there too, maybe 13% or so.
Okay.
And copper. Now, copper's interesting. Older types didn't have much, but modern ones, they often have a lot more. High copper, they call them.
High copper. Right. We'll come back to that. Anything else?
Sometimes a little bit of zinc, yeah. It has a specific job, but also a potential downside we need to talk about.
Okay, but let's hit the big one first. Mercury. 50%. That's the thing that, makes people uneasy. The whole mercury scare. Why use it at all?
That's a super important question. The reason mercury is absolutely essential is its unique property. It's a liquid metal at room temperature.
Right. You can't just squish a solid chunk of metal into a tooth cavity.
Exactly. Impossible. So mercury acts almost like a solvent for the other metal particles, the silver, tin, copper, maybe zinc.
It dissolves them?
Well, it wets their surfaces and starts to dissolve the outer layers. This creates this soft, pliable, putty-like mass.
Ah, so that's how the dentist can shape it into the tooth?
Precisely. They can pack it in, adapt it to all the little corners. That whole process, the mercury mixing and reacting, that's called amalgamation.
Okay, makes sense. It gives you the workability.
Yeah.
But then how does it get hard? It doesn't stay like putty, obviously.
No, definitely not. As the mercury interacts with those alloy particles, a chemical reaction kicks off.
A reaction inside the tooth.
Yep. New compounds start forming compounds containing mercury, and these new compounds are solid. They crystallize and grow, using up the liquid mercury.
So less liquid mercury means it gets harder.
Exactly. The mass solidifies as these new phases form and interlock. That's where the strength comes from. It's a chemical transformation from liquid plus powder to a solid structure.
That's actually pretty cool. So mercury is vital for making it workable and becomes part of the final solid filling. Okay, let's break down those other metals. Silver, what's its job?
Silver is a major player. It adds quite a bit of strength, number one. It also makes the amalgam set faster, which is good
Better
planetary.
setting, okay.
And it helps whiten the alloy, makes it look more silvery. Plus, it decreases something called creep, we'll define, that later increases tarnish resistance and, interestingly, causes a slight expansion as it sets.
Wow, silver does a lot. Sounds like the backbone. What about tin? You said it's in there too.
Tin? Well, tin kind of does the opposite in some ways. It actually tends to reduce the strength and hardness a bit
Reduce the strength? Why have it then?
because it also controls the setting expansion. It reduces expansion, kind of counteracting the silver a bit. It's all about achieving a balance for the right overall properties.
Ah, okay. A balancing act. Makes sense. And copper. You mentioned modern amalgams are often high copper. What's the big deal with copper?
Copper is really important, especially in the newer formulations. It significantly boosts strength and hardness, even more than silver in some ways.
Okay.
And crucially, it dramatically reduces that creep phenomenon we mentioned. Like silver, it also contributes a bit to setting expansion. The high copper content is a key reason modern amalgams perform so much better.
So listeners, take note. That silver filling you might get today is probably a high copper one, and that copper makes a big difference in how strong and long-lasting it is compared to older types.
Absolutely, it was a major advancement.
Okay, last one. Zinc. What does zinc do?
Zinc's primary role is actually during manufacturing the alloy powder. It acts like a scavenger, grabbing onto oxygen to prevent the other metals from oxidizing too much.
So it helps make a cleaner powder.
Sort of, yeah.
Yeah.
But here's the critical thing about zinc in the filling itself. Moisture contamination. If saliva gets mixed in while the dentist is placing a zinc-containing amalgam, big problem.
Oh. What happens? You mentioned a downside.
It can cause something called delayed expansion. It doesn't happen right away, maybe starts 3 to 5 days later.
Delayed expansion. That
Yeah.
sounds really problematic.
It is. The zinc reacts with water, the
Hmm.
moisture, and produces hydrogen gas. Tiny bubbles of gas trapped inside the setting amalgam.
Gas inside the filling.
Yeah, and that gas pressure causes the filling to expand, sometimes quite significantly, like up to 4%.
Oh.
This can cause pain, pressure, even crack the tooth.
Wow. So keeping the tooth dry during placement is absolutely vital if there's zinc involved.
Absolutely essential. That's why dentists use things like a rubber dam, that sheet that isolates the tooth. It's not just for convenience. For zinc amalgams, it prevents this potentially damaging expansion. Critical insight there.
Man, that really drives home how technique sensitive this stuff is. Okay, so composition is key. Now, the video mentioned different types based on the alloy particle shape. Lathe cut, spherical. What's that about?
Right. So think about the powder itself. The little bits of metal alloy before the mercury is added.
Yeah.
They can have different shapes.
Okay.
Lathe-cut particles are made by basically milling or shaving an ingot of the alloy. They end up being irregular, jagged little pieces, like tiny metal filing.
Irregular shape. Got it.
Because they're irregular, they have a relatively high surface area for their volume. More nooks and crannies.
And why does that matter?
More surface area means you need more mercury to wet all those surfaces and start the reaction properly to get that workable mix.
Ah, okay. More mercury needed for lathe cut. What about spherical?
Spherical particles are just what they sound like. Tiny, round balls. They're made by spraying the molten alloy into an inert gas chamber, and the droplets solidify as spheres.
Smooth little ball.
Exactly. And because they're smooth spheres, they have the lowest possible surface area for their volume.
So they need less mercury.
Precisely. Less mercury is needed to coat them, which can be an advantage. Spherical alloys also tend to feel very smooth and plastic when you're working with them.
Easier to place, maybe? But you hinted there might be a catch, especially for fillings between back teeth. Class 2, right?
You got it. The downside is because they're so smooth, like tiny ball bearings.
Yeah.
They don't offer much resistance when the dentist is packing the amalgam in condensing it. It's easy to push them too hard, especially sideways.
So they might squish out where you don't want them?
Right. You can get overhangs, little ledges of filling sticking out, or it can be hard to press them firmly enough against the next tooth to create a nice tight contact point. That's a problem for class 2s.
Makes total sense, like trying to build a wall with marbles.
Yeah.
So what's the third type? Admixed.
Admixed is the clever solution. It's a mix. It contains both lathe-cut and spherical particles.
Best of both worlds.
That's the idea. The irregular lathe-cut particles provide some body and resistance to condensation, helping you build those contours and tight contacts, especially in class 2. While the spherical particles still contribute to a generally smooth feel and can help keep the overall mercury content lower than a pure lathe cut. Admixed high copper alloys are actually super popular for this reason.
Fascinating. Just the shape makes such a difference in handling. What about particle size? Does that matter too?
It does play a role, yeah. Modern powders are tiny. We're talking micrometers, like 15 to 35 Vem.
Really small.
Generally, if you have smaller particles, you have more total surface area for the same amount of alloy.
Okay, so smally particles again mean more mercury needed.
Usually, yes. And they might set a bit faster, get strong quicker. But sometimes really fine particles can lead to a slightly rougher final surface, maybe more prone to corrosion down the line.
A trade-off. What about bigger particles?
Larger particles need less mercury. But the risk there is during carving shaping the filling. A larger particle near the edge might get pulled out by the carving instrument.
And even a little pit.
Exactly. Which again makes the surface rougher and potentially more prone to corrosion. So most modern powders are actually a blend of sizes, trying to hit that sweet spot for handling and final properties.
Man, it's complex. Okay, let's talk chemistry, the reaction itself. You mentioned gamma 1 and gamma 2 phases, especially in older, low copper amalgams. Can you simplify that?
I'll try. So
Yeah.
in those traditional low copper types, when mercury mixes with the silver and tin,
Yeah.
two main new things form. One is called gamma 1, that's a silver mercury compound. Pretty stable stuff.
Okay.
The other is gamma 2, that's a tin mercury compound. And that's the problem, child?
Gamma 2 is bad. Why?
It's just inherently the weakest part of the set amalgam. It's also much more susceptible to corrosion breaking down chemically in the mouth, and it contributes significantly to that creep, the slow deformation we talked about.
So the Achilles heel of old amalgam was this gamma 2 phase.
Pretty much. It limited the lifespan and performance. This is the key thing that high copper alloys were designed to fix.
Okay, so how do high copper alloys fix the gamma 2 problem?
It's clever chemistry. Copper, it turns out, really likes to react with tin, more than mercury does, actually.
Okay.
So in a high copper alloy, when the reaction starts, the abundant copper essentially grabs the tin before the mercury can.
It intercepts the pin.
Basically, yeah. It reacts with the tin to form a copper-tin compound instead called the eta phase.
And no tin left for the mercury to make gamma 2.
Exactly. It drastically reduces or practically eliminates the formation of that weak, corrosion-prone gamma 2. That's the magic. Better strength, way less creep, better corrosion resistance. It all comes back to getting rid of gamma 2.
That's a fantastic bit of material science right there. Okay, shifting to the dentist's chair now, mixing it up. Trituration and the mercury alloy ratio. Why are these so critical?
The ratio is fundamental.
Yeah.
You need just enough mercury to wet all the particles and create that plastic workable mass.
Not too much, not too little. Goldilocks principle.
Exactly. Too much mercury. The final filling will be weaker, more prone to fracture over time. Too little mercury. The mix is dry, crumbly, impossible to adapt properly, and also weak and likely to corrode.
Got it. What are the typical ratios these days? You said spherical needs less.
Right. Old lathe cuts were around 50% mercury. Sphericals might be down around 42%. But honestly, the biggest thing now is pre-proportioned capsules.
Single dose things.
Yeah. They take the guesswork out. The manufacturer puts exactly the right amount of powder and mercury in a capsule, sealed up, ensures consistency.
Makes sense. And trituration, that's the shaking, right? In that special machine.
Yep. The mechanical triturator or amalgamator, it shakes the capsule really fast, oscillates it to thoroughly mix the liquid mercury and the alloy powder. We're long past dentists mixing it by hand with a mortar and pestle.
Thank goodness. How does the dentist know if the mix is right?
The consistency is the key visual cue. A perfect mix, optimally triturated, looks smooth, plastic, kind of holds together as a single mass. Should have a slight sheen or luster.
Okay. What if it's undermixed?
Under trituration, not mixed long enough or fast enough, gives you a grainy, crumbly mix that looks dull. That mix will be weak and leave a rough surface, more tarnish later.
And overmixing, too much shaking.
Over-trituration makes it too soft, almost soupy or mushy. It might stick to the inside of the capsule, look really shiny and wet. It often sets faster, gives you less working time, and can actually contract a bit more when it sets.
So getting that trituration just right, time and speed, is crucial for the final quality. Like baking, you said.
Absolutely. Critical step.
Okay, mixed right. Next step, condensation. Packing it into the tooth. What's the main goal here?
Goal number one is density. You want to pack it in as tightly as possible, eliminating any voids or air gaps. That maximizes strength.
Okay, density. What else?
And adaptation. You need to push it firmly against all the walls and especially the edges, the margins of the cavity prep. A tight seal is vital for preventing leaks and recurrent decay.
The video mentions seeing a shiny surface on each layer as you pack it. Why is that shine important?
That shininess tells you there's a little bit of unreacted mercury still available at the surface of the layer you just packed.
And that's good.
It's essential. It allows the next scoop of fresh amalgam you add to chemically bond to the layer underneath. It helps make the whole filling one solid, continuous mass, not just separate layers stuck together weakly.
Okay. Makes sense. Does the size of the packing instrument, the condenser, matter?
Big time. Pressure equals force divided by area, right? So a smaller condenser tip concentrates the packing force into a smaller area, creating higher pressure.
So smaller tip, more packing power.
Generally, yes. You need that higher pressure to really adapt the amalgam well, especially into sharp corners or deeper parts of the prep. Using too large a condenser might feel like you're pushing hard, but the pressure might be too low for good compaction. Leads to voids, weaker filling.
And we have to think about particle shape again here, don't we? The sphericals.
Yep, back to the slippery spheres. Because they offer less resistance, it's easier to push them too far, especially sideways in those Class 2 boxes. Harder to build a good contour and contact point. More risk of overhangs.
Which is why admixed is often preferred for those.
Exactly. The lathe cut bits in admixed give it more body to resist the packing forces better.
Okay, packed tight. Now carving, shaping it like a tooth. What's key here?
You want to recreate the tooth's functional anatomy, the cusps and grooves needed for chewing. But, crucially, don't carve too deep,
Why not?
because you can thin out the amalgam too much in certain areas, creating weak spots that might fracture later under biting forces. You need enough bulk for strength.
And timing is important. Don't carve too soon.
Definitely wait until it starts to harden up a bit. If it's still really soft and plastic, the carving instrument can just pull material away, especially at the edges, creating gaps or open margins. You need it firm enough to cut cleanly.
What about that metal band around the side for class 2, the matrix band? When does that come off?
Usually you take the matrix band off carefully during the final stages of carving. That allows you to properly shape that side surface and make sure there's a smooth transition from filling to tooth.
Got it. Final step. Polishing. Why polish and when?
Polishing makes the surface really smooth and shiny. That's important for a couple of reasons.
Like what?
One, plaque and food debris don't stick as easily to a smooth surface, so it's easier to keep clean. Two, a smoother surface has less area exposed and fewer rough spots, which makes it less likely to tarnish or corrode over time.
Makes sense. But you don't polish it right away, do you?
No, absolutely not. You need to wait at least 24 hours or often until the next appointment. The amalgam needs time to fully set and gain strength.
Polishing too soon would mess it up.
It could interfere with the final stages of the setting reaction and potentially weaken the surface. Plus, polishing generates some heat, and you want to avoid heating up freshly placed amalgam.
So patience required. Use water spray during polishing too, right? To keep it cool.
Exactly. Gentle technique, water coolant, usually with rubber cups or points. Avoid overheating it.
Okay, great. Let's shift to the properties of the set amalgam, how it behaves long term. Dimensional change. The video said modern ones tend to contract slightly, not expand.
That's right. Our understanding has shifted. While very old formulas might have expanded, most modern high copper amalgams show a small net contraction as they set.
Why do they contract?
It's because the final volume of the solid reaction products, the gamma-1 and eta phases, is slightly less than the original volume of the mercury plus the alloy powder. Using less mercury and packing it harder tends to increase this contraction slightly.
But what about that delayed expansion with zinc and moisture? That sounds like the opposite.
It is the opposite, but it's a totally different mechanism. The slight setting contraction is inherent to the normal chemical reaction. The delayed expansion is an abnormal reaction caused specifically by water contamination of zinc.
Ah, okay.
Yeah.
Normal setting, slight shrink. Bad technique with zinc plus water equals big delete expansion.
You got it. Two separate things. Proper technique avoids the nasty expansion.
Right. Next property, strength. Amalgam strong in compression, weak in tension, like concrete.
Good analogy. Very strong when you squeeze it, compression, but much weaker if you try to pull it apart or bend it, tension or tensile strength.
How does that affect how fillings are designed?
Dentists design the cavity prep to minimize tensile stresses on the filling. That's why amalgam preps often look like boxes with flat floors and relatively sharp 90-degree angles at the edges. Cavity surface margins.
To make sure the biting force is mostly just pushed down on it.
Exactly, to load it in compression where it's strongest. And of course, proper mixing, ratio, and condensation are all vital to achieve the maximum potential strength. Mistakes there weaken it.
Okay, now let's talk creep again, that slow deformation. The video linked it to marginal breakdown, the edges crumbling over time.
Yes, particularly in the older low-copper amalgams. Creep is that slow flow or distortion of the material under repeated low-level stress, like chewing after it's already set.
And the gamma-2 phase was the culprit.
It was a major factor. Low-copper amalgams with lots of gamma-2 had much higher creep rates. Over years, this slow flow could cause the amalgam to bulge slightly out of the prep at the margins.
Making it stick out a bit.
Yeah, and then those thin, extruded edges are weak and prone to fracturing off, leaving that ditched or broken down margin you see on old fillings.
So high copper alloys, by getting rid of gamma-2, have much less creep.
Significantly less creep. That's a huge reason why their margins tend to hold up so much better over the long haul. Better edge integrity.
Makes sense. Okay, finally, tarnish and corrosion. What's the difference, and how do they affect the filling?
Tarnish is just a surface thing, discoloration, often sulfide forming, making it look dull or black. Usually it's just cosmetic, doesn't really hurt the filling's function.
So tarnish isn't great looking, but not structurally bad.
Generally, no. But it can sometimes be a sign that conditions are right for corrosion. which is bad. Corrosion is the actual chemical breakdown of the amalgam itself.
What breaks down?
In low copper amalgams, it's often that gamma-2 phase again. It breaks down, forming tin oxides, tin chlorides. Basically, the filling degrades. This weakens it, contributes to marginal breakdown, and can lead to failure.
And high copper alloys are better here too, because no gamma 2.
Much better. The eta phase, copper tin, that forms instead, is far more corrosion resistant. Plus, a smooth, well-polished surface resists both tarnish and corrosion better, regardless of the alloy type. Okay, now for the really surprising part from the video, leakage around fillings can decrease over time. How does that work?
Isn't that weird? It seems totally backwards. But what happens is, as the amalgam sits in the mouth, some of those corrosion products we just talked about.
Yeah, the stuff breaking down.
Some of those corrosion products actually precipitate and deposit themselves right into the microscopic gap that exists between the filling and the tooth wall.
They fill in the gap, like rust sealing a leaky pipe.
Kind of like that, yeah. Over time, these corrosion products can essentially seal off that interface, reducing the microleakage that might have been present initially.
Wow. So a little bit of corrosion in the specific way can actually be beneficial.
In terms of sealing the margin over the long term, yes. It's a unique property of amalgam compared to, say, bonded composite fillings, which rely on the bond staying intact. That is definitely a fascinating twist. Okay, let's try and wrap this up. This deep dive really showed that dental amalgam is way more than just a simple silver filling.
Absolutely. It's a carefully engineered alloy. Mercury's role is complex, but vital.
And the specific metals, especially getting that high copper content to kill off gamma 2, make a huge difference.
Huge difference in performance, yeah. Less creep, less corrosion.
And the dentist's technique, mixing, packing, carving, polishing every step, is just critical for success.
And to be more critical, technique sensitivity is high.
Plus, we learned about the risk of moisture with zinc and that amazing fact about leakage decreasing over time due to corrosion products.
Yeah, that sealing effect is pretty unique.
It really gives you a new appreciation for this material, doesn't it? Even if you're not in dentistry, knowing these details is pretty valuable insight.
Definitely. It's been a mainstay for a reason, even with newer materials available.
So it makes you wonder, with all the new stuff coming out, composites and ceramics and all that, what is the future for amalgam?
That's the million-dollar question, isn't it? It's constantly being evaluated.
And maybe knowing all this complexity now, does it change how you think about those silver fillings you might have or see in others? That balance between old, reliable, and new tech. It's definitely food for thought.
It is. Material science in dentistry is always moving, always balancing factors like longevity, aesthetics, cost, ease of use. It's a fascinating field.
Truly is. Well, that's all the time we have for this deep dive into dental amalgam. Hope you found it as interesting as we did.
Yeah, hope it was useful.
If you've got more questions or ideas for other materials, maybe composites next time, let us know. Until then, keep smiling, stay curious.